All right, so to end this cute little section on these non-deterministic machines with these epsilon transitions, I actually want to revisit one of the machines that you guys have actually built up in one of your activities. Maybe you're working on that activity right now and you're getting some spoiler alerts, but whatever, you'll see it again, so hooray. Anyway, so the machine in question is going to be that plays with nice little bit strings, so an alphabet of zeros and ones. And one of the things it's going to accept are going to be those that have an even number of zeros or exactly two ones. So you can kind of already see that there's going to be a split ski happening. And I'm going to show that the epsilon transitions make that split ski really, really easy. So before we do that, let's kind of revisit the nice little deterministic machine that actually plays with this set and just kind of think through some things that are going to be accepted and possibly rejected. So an accept bin would be something like 0, 0, obviously an even number of zeros. So would 0, 0, 1, 0, 0, an even number of zeros. 0, 0, 1, 1, 0, 0, that has an even number of zeros and it has exactly two ones. We'd also have things like 1, 1, 1, 0, 0, which has an even number of zeros, but it does not have exactly two ones, but it doesn't need two ones. It just has three of them. On the other side, you can have, well, two ones and then any number of zeros that you want to pad around this thing. As long as you have exactly two ones, life is great. So obviously just 1, 1 works as well. So from the initial onset, you might think that this should be really easy to design. You're like, okay, that's not very hard requirements to have an even number of zeros. We've built up machines for that. And containing exactly two ones, that's also pretty easy. What's unfortunate here is when you try to merge these things together, you end up getting a machine that has like 8 overall states, which is kind of unfortunate and looks really unpleasant. Or you're like, why does it take so much? So let's revisit that little 8-state machine to see how that's going to pan out. So along the way, we're going to have a couple little like helper machines. So we're going to have a machine that accepts an even number of zeros. So we just basically start with an even number of zeros if I have no zeros, and then I leave that state anytime I have a zero. And then I come back to it if I find a zero again. So every zero basically has to have a friend. So I leave and then I come back if I have a friend. I leave and I come back if I have a friend. So if I wanted to work through something like 1, 0, 0, 1, 0, 1, 0, I'd spin on 1, I'd leave on 0, I'd come back on 0, I'd spin on 1, I'd leave on 0, and then I'd actually spin on the right side and then come back on the 0, which ends me up at an even number of zeros. So life is great. The bottom one is then going to be a machine that accepts exactly 2 zeros. And you can see that that machine does exactly that. Is that you're moving on the first 0, you move on the second 0, and life is great. Is that you can have as many extra, or you move on the first one, you move on the second one, and you can have as many zeros along the way as you ever want. So exactly 2 ones. Man, 2 typos today. Hard day, I guess. All right, so we move on exactly ones, and we try to get to that end point on that one, and everything is great. All right, so if I tried to merge these things together, I like to think about this as some kind of cute little road structure. So what that's going to look like is everything on the left is going to basically keep track of my even or oddness of my zeros. So if I'm on the left side of the road, I'm correct on my zeros. If I go across the street, I'm going to pick up a 0 and it's going to switch it to having an odd number of zeros. So that's going to be an unfortunate world most of the time. So the left-right movement is then going to be on the zeros, going from even to odd. The vertical movements, which are all going to be downward, are then going to occur whenever I read a 1. So if I were to see an input of 0, 1, 0, 0, 0, you would then see that I move down on the 1. Oops. I move across on the 0, down on the 1, back on the 0, forwards, backwards, which lands me right there. So I would accept that particular input. So the vertical movement's always going to happen on the 1s, and it's basically trying to get us into that row of having exactly 2 1s. So exactly 2 1s happens right there. So I don't care what the 0 structures happen to be. Here we're in kind of the holy grail is that we have an even number of zeros and we have exactly 2 1s. So life is great there. But if you have any additional 1s after that, you're going to go down and basically have no chance of ever satisfying the exactly 2 1s requirement. But you can still satisfy the even number of zeros. So you get this kind of 4x2 or 2x4, depending on how you're viewing this particular structure, that's going to keep track of the evenness of the zeros on the left side, so therefore the oddness on the right side. And then the number of ones is going to be the number of clicks downward. So 1, 1, 2, 1, or possibly 3 or more ones down on the bottom. So that little machine is nice. It's actually deterministic, and it's going to play nicely with this particular set. So the question we have is then, could we possibly do better with some epsilon transitions? So these epsilon transitions very nicely split the OR into 2 bins. And that's exactly what I'm going to do here. So I'm going to use those 2 little helper machines that we had before. So keeping track of the even number of zeros, or exactly 2 ones. And I'm going to basically glue them at the end of this fork, where the fork has 2 little epsilons. So if I wanted to play with something that looked like 1, 0, 0, well, what's going to happen is that I'm going to come on down. I can go either way for free. So if I went to the left, I would read the 1, I'd go down on the 0, and I'd come back up, which actually puts me into an accepting state. So you'd see that this machine accepts it, but I could technically have gone the other way too. So if I came across on the epsilon, if I read the 1 and then spun, it puts me into a non-accepting state over there. But as long as one of them puts me into accepting, life is awesome. So I can actually accept the input of 1, 0, 0. If I wanted to look at something like 1, 0, 0, 0, you can see that that 1 would come down here, come across. I could spin on the 1, come down, up, and down, which is a non-accepting state. And on the other side, it'd go here, down on the 1, 1, 2, 3, again in a non-accepting state. So that thing would then be rejected. So what's cute about it is you can easily take those little helper machines. Basically, if you can design the helper machines and then you just kind of dangle them off a couple of these epsilon transitions, and you have a really cheap way to create some of these machines that do some more exotic things. So we have these nice little teleporters. Obviously, that's a non-deterministic machine with epsilon transitions, but we know that we could reconvert that thing into a deterministic one. We probably wouldn't have it reconvert into this one if we ran that process, but we could convert it into a deterministic machine. So again, these epsilon transitions don't give us anything extra. They sometimes just make our lives a little bit easier when it comes to designing them. So it's kind of a good practice to try to see how few states you can actually use and play this game and try to be like, well, do I really need that? Could I get by with an epsilon transition, or could I do something else entirely? And that's where it gets kind of really fun and exciting when you're trying to bash your brains in on, making things as elegant as possible. Sometimes they're just going to be gross, kind of like this one. Other times you can at least improve them a little bit. Other ones you can get some really, really tremendous improvements with these little epsilon transitions.